So good morning to many students here in the lecture hall. It's quite windy today. This is a tutorial, as you know, and we start with task number 4. You should really see the tasks, otherwise it doesn't make sense. Yeah? So, you know, the task collection is on the Moodle page. Okay, so we start. I switch off here the can't see me really. Okay, then let's start. As I said, task number 4, task collection. So 4. And then you can see this picture, consider 2 as a feedback. Maybe there is a microphone switched on from the WebEx participants. Exactly where this comes from. So task number 4, you see we consider 2 random variables. Let's say one random variable is denoted as x, the other as y. And x can take the values 0 and 1. Y can also take the values 0 and 1, like this. Then, as it written on the picture, probability that x is 0 is just 0.2. The probability that y is 0 is just 0.3, as you can see. And then we have here, the arrows show the conditional probabilities in this state diagram. So, and here we have the probability that for a given x equal to 0, what's the probability that y is also 0? 0. So this is the conditional probability P, y given x, 0, 0. Can't do anything to compensate this feedback here. For. It's written that Hussein wants to show tent. Don't know what this is. Oh, maybe he writes me in the chat. Yeah. So this is the probability is 0.7. And then it's quite easy. I don't think that you think a lot about this. So what's the probability that x is equal to 1? 8, of course. So we can, this is a complete probabilities marked by the questions. So this is 0.8. Sorry for this. Basically sometimes. And this is, of course, 0.7. Now it's more difficult, say, to complete the additional probabilities, of course. But one conditional probability is very easy, and this is this conditional probability. So this is A, yeah? So everything for A is in green. Yeah? What's the conditional probability that y is 1 given that x is 0? It's quite easy. 0.3, right? Because the sum of all outgoing probabilities needs to be 1. Yeah? So if x is 0, y needs to be either 0 or 1. And the probability that if x is 0, y is 0 is 0.7. So this is 0.3, of course. This is not difficult. Then it's more difficult, probably, to calculate the probability in this direction here. So this probability. So we could start with this. This is, of course, if I write this, just for those which have problems, this is this probability, of course. The question is, how large is it? This probability. Is there any idea how could you calculate this probability? Yeah?
Hello.
Yes, exactly.
Sir, we can apply matrix method. That is, receiver matrix is equal to product of your transmitter matrix and channel matrix.
Yes.
Channel matrix is nothing but conditional probability matrix.
Of course, yes, you're right. I mean, we do not need to interpret this at the moment as a channel. We could do this, yeah, we could say this is what we transmit, this we could say this is what we receive. At the moment, we only see two random variables and conditional probabilities. But of course, you're right. I write it here. If we say we have this state y is equal to 0, let's say I write this as in our notation. So the probability that y is 0 is, of course, I mean, we can come to this state only from here and from here. So we could say this is px is equal to 0 times the conditional probability, 0, yeah, plus, and then we come from x equal to 1, multiply this with the conditional probability of y 0, 1. And this is what we are looking for, of course. Yeah. Now I just insert the numbers, as you said. Maybe I write this like this here again. So this is 0.3. This is equal to 0.2, which was given, times 0.7, plus, and now the probability that x is 1, 0.8 times probability we are looking for. Now we just can calculate this. So this is 0.14, right? So we can say that, let's say I write this like this, P given x of what we are looking for is equal to 0.3, 0.4 by 0. So, and this is 0.16 divided 0.8. So, and this should be 0.2, of course. Yeah, 16 divided. So now we have it and can write here, this is this here, yeah. So 0.2. Yeah. And then there's no question about this probability. Then it's quite easy because we see this needs to be 0. But this was the only thing which was difficult. It's like here. This is what we can. So this is A. Now you can calculate on your own just part B. This is quite simple, yeah. The entropy of X and the entropy of Y. So what is the entropy of X? Doesn't work. Entropy of X. Is it? What is the entropy of Y? This would be C. You can do it on your own. You need to use calculators, otherwise you can write the expression for the first, yeah. Then you need to use a calculator. So I can have a look. I'm not sure if MATLAB is installed here on this computer. I don't think so, but possibly it is the case. I don't know. With MATLAB, it's quite easy to, yeah. Math input, MATLAB, Matrizen, It's not installed. Ah, MATLAB. Maybe I start this, see what happens. Oh, no. There's no start in MATLAB. It's just done it page. It's not installed here on the computer. Otherwise, I mean, if I use here the calculator, this is stupid. But I advise to you, just write it here, that you install a program which is called Octave. Octave. This is just for free. You can use it in Linux. You can use it in Windows as you want. Yeah? Whatever, possibly in Mac, I don't know. It's called Octave, and it has basically the same syntax as MATLAB. And it's quite advantageously for communications engineering. Or, for instance, results. Yeah. But you can also use Python, of course. Yeah. So, and then you rewrite here. You don't have to think about this if you understand the concept. Yeah. So we take a look at information content of the state 0, and this only depends on the probability. It's minus log2 of 2, and then we weight this with the probability, yeah? And then we do the same with the other state. Probability is 0.8. Weight this with 0.8. And of course, you do a logarithm. If you use a calculator, take care, yeah? And then what comes out should be, if you calculate this, it's approximately 0.72 about. It's an approximation. Yeah, and of course, here I need to write, but always try it on your own. By the way, there is another task. You can try it on your own. This, let's say, homework. I write it here, right? Can present the results, homework. It's really the same task, basically, but for other numbers. This is number 3. Looks like this task, but at the output, we have 3 states in this homework. So now I come back. So this is, of course, 0.3. Take a look at the probabilities here, 0.3 and 0.7 times log 2. Yeah, there was an answer, really good already. And I can just copy this from the chat. 0.8 plus, 0.3. 0.7 times log 2 of 0.7. This is approximately, as it is written, correctly written, very good. If you write, you can really write bit per symbol, yeah? Because it's an average, on average per symbol. As it's written here in chat. So I just check if this result, if I got the same result. Yes, I got the same result, yeah. So, and then in D, yeah, it's asked for the joint probability mass function and sketch a figure of this probability mass function. Of course, in D, you can try it. How can we calculate, for instance, p x comma y of 0 and 0? So what's the probability that we that x is 0 and y is 0? And given the probabilities that we have, can of course write this is px of 0 times py given x of 0, 0. Yeah, it's clear. So what do we get at the end? We get, of course, 0.2 times 0.7, and this is 0.14, right? So this is the first, and you can calculate the others. So P 0 and 1 is equal to here y of 1 and 0, and here p x y 1. Just try it on your own. There is there is a person above sharp. I don't know how to spell this. Is this from Kazan? Does it sound like?
Sir, I am from India.
Okay, so you can already read some probabilities here. Yeah, of course. If you, what is the probability that x is 0 and y is 1? So this would be this and this. Yeah, 0.06, right? 0.06. Yeah. So if I add this to this probability, it's 0.2. So the sum of these two probabilities should be 0.8. Yeah. So and then 1 and 0, it's 0.8 times 0.2, 0.6. So and this is 0.8 times 0.8, 0.0. So this is in total 0. Now we can even draw a figure if you want, yeah, of this probability, joint probability mass function. Let's say we have yeah. Let's say we have here y. Let's say that we have, this is our probability. So now I draw it in, let's say, red. Yeah, so I write this is x. This is the value of y. So lowercase, of course. This is p. So now there are only two values for both variables. One value is 0, it's 1. One value is 0, and the other is 1, let's say. This would be. So and then we could, I do it in red, yes? So 0 is 0.14. Let's say this is, or this, that it's more or less in the right proportion, yeah? Try to change this. So let's say 0.14 is this height. Approximately. This is 0.4. So then we have this, x is 0, and y is 1. As you can see, this is 0.06, yeah? It's very low. It's here. 0.6 is about half of this height. So let's say it's like this. 0.6. Then we have x as 1 and y is 0 is 0.16. So it's a little bit higher than 10. So if you want, you can write here somehow 6. And the other has the highest probability, 1 is 0.64. Whatever. 64. So it's, of course, two-dimensional, yeah, to draw here. Okay, now it's written, determine the joint entropy h of x and y. And now we use this joint probability mass function, of course. We use these joint probabilities. And you can do it again on your own. So what is h of x, comma, y? But this is not task, I mean, difficult to ask. Because now you say, I use the old equation of entropy. The same equation is for a one-dimensional but you just use the joint probabilities. So what is the surprise of certain combinations? Is equal to, you can do it on your own.
Hello, sir.
Yes?
Sir, in this case, it is given that they are
Can you, sorry. Can you increase the distance to your microphone or make
okay,
it
okay, okay.
quieter? That's good. Now it's
Okay.
good.
Sir, it is given that they are two statistically independent random variables.
What?
Okay. Sir, in the question, it is given statistically dependent random variable is given.
I can't understand you. Sorry. I mean, not from the level, just, sorry, can you repeat slow?
Sir, it is given in the question that they are there are two statistically sorry, it is dependent. Okay, okay.
Okay.
I understood it, right?
Okay. Of course, we have to insert just these probabilities we calculated before. So is this minus sign, yeah? 0.1 log 2, 0.14, 0.6 times 2, 6, 6 times plus 0.64 times log 2 of 0.64. It's quite nice because I can see the result here in chat. This is, I just checked this, if it's correct, but it seems to be correct. 1.4 is exactly result. So 1.6, very good. If you want, write just bit per symbol. So this is E, and now we can go to part number F, yeah, and try it on your own. No, this was E, yes, F. Now we are looking for the conditional probabilities just in the opposite direction, as you can see. So in this figure here above, yeah, have the conditional probabilities of y given x. Of course, we can also calculate in the other direction. This is just training for you. So what we are interested in is basically, let's say I draw it, 0, 1. So this is x. This is 0.2, as you can see. This is 0.8. This is 1. 0 and 1, sorry. 0 and 1. This is y, this is x, this is y. 3, 0.7. And we have the joint probabilities. This is what we need. So we have px. This is what we have. Now we are looking, for instance, for this probability. If once we have this probability, let's say we start with this, then we can calculate this is easy, because the sum of the outgoing probabilities needs to be 1. And then let's say in the next step we calculate this probability, or whatever which probability. But let's say you start with this. So we're looking for px given y of, what is it, 0, 0. Try to find this. We have the joint probability, so it's quite easy to calculate this. Just try it on your own. You are quite fast. Are these the probabilities? Yes. Yes, it's correct. But I give the others some time. So, okay, then could we calculate this? I mean, we used the same before, If we say, for instance, p x comma y, to the joint probability of x and y. Also say, if we know y, certain y, multiply this with conditional probability given y, we have t of the combination. Therefore, we can say p So 0. This is, of course, the probability, the joint probability. So the joint probability of 0 and 0 is 0.14. Divide this by this probability of 0.3. Divide by 0.3, and this is, I have to look, 0.66. Just have to look in chat. This is quite, it's an approximation, of course. And then if we know this probability, then this probability, of course, is quite easy this way. Again, I write here, so this is what we calculated first, and then we write here 0.4666, and this is 0.53333. Yeah? Because the sum of these two probabilities needs to be 1. Then again, let's say we do this for the green probability, so P of, so y is, x is, let's say, 1, y is 0. This is the probability of joint probability, that x is 1 and y is 0. So this is this, 0.6, right? You have to correct me if I do an error, yeah? Divided by the probability of this y, and this is again, so the green is 1, 1, of course. Wanted to calculate this one, yeah? I looked here, but we wanted to calculate this 1, 1. This is 6, 4, right? This one. 1 and 1 has 6, 4 as joint probability, and then this probability is 0.7. Yeah, this is quite large values. 4. Approximately. So this is 0.14. And this probability, of course, this direction is just, yeah, I have to add a 6, yeah, to this 4, then it's 1, then this is 8. That's right. I mean, all these are approximations, of course. So this is F, basically. So, and now I calculate the conditional entropies, yeah. Of course, this task, I mean, you have different ways to calculate this. Simplest way at the moment, of course, because we have already the joint probability, is to say, okay, maybe we start with this, yeah, we make a diagram, and say, start with h of x. Oh, just want to draw a circle. Doesn't it work? This is h of x, okay. So h of y is larger. Why is it larger? Because this is 0.2, 0.8. This is closer to an equally distributed, yeah, case with an equally distributed. Say now, we make this a little bit larger. Say it looks like this. Then what do we mean? This is h of x. This is h of x. Yeah, the red is h of y. What we are looking for is for h of x given y. But we can also calculate h of y given x. Yeah. So this is, of course, h of x. And let's say I draw here, so this is green. This is, of course, you can see here. So this is h of y given x. Let's say I have such a green x given y. And of course, this here, maybe I do it in black, yeah, black. Black. This is of course the joint probability, the joint entropy. This one, yeah, that's the joint entropy. What's it? X and y. Then it's easy to calculate these values just if we know the joint entropy. If we know the joint entropy, of course, we can calculate, say, this one, h of y gives, this is just h of x and y, yeah. Black one. H of x and y minus, yeah. So this is the total, yeah. Want to have this h of x, of course. So it's a surprise in y if you know x. Minus h of x, and this is. And we can also say, then we can write here the value, of course. And then we can do the same for this special color here. Let's say it's this. Sure if this is this color. Let's say here h of x given. This is again this black one. And y. And then to the h of y is equal to. So I don't know if I calculated both, but there shouldn't be a large problem. So this is, if we calculate this one, this here of IH given x is 0.7538, and x given y, don't have it, x given y. And write this in the, yes, but maybe you just calculate this for me. Otherwise, I have to use the calculator here. What is it? Can you tell me? 0 point, sorry, 0, 5, 9, 5944. And of course, this was the fastest way, yeah, to obtain this, because we already calculated the joint entropy. But of course, if you want to do this, yeah, you can say there is an opposite way, which is to directly calculate the conditional entropy by means of the conditionalities, of course. The idea is, of course, to say, yeah, let's say I do this for h of alternative way. Let's say we write this alternative. Could say, we can say h of y given x. So both are capital letters, yeah. This is. So let's say 0.2, yeah, and this 0.2 is just this probability that x is 0. And then we write here conditional entropy of y. If this x is 0.2 plus 0.8 times conditional entropy of y, this capital Y, for this special value of x, 0. Then we have to calculate this. This only depends on the conditional probabilities, and this only depends on the conditional. So we can say h of y given is 0.2 only depends on these conditional probabilities. And we remember, if we took a look at the arrows, at these conditional probabilities, one conditional probability is 0.7. So the surprise is log 2, 0.7, and here, of course, 0.7, plus 0.3 times log 2 of 0.3. But these two probabilities have nothing to do, of course, with 0.3 and 0.7. It's this, this 0.7 and this 0.3, of course. Conditional probabilities, yeah. So then we can calculate this, yeah. And of course, at the end, we get the same result for this h of y given x. Then we calculate this. It's this one. Then we have to weight these conditional probabilities at the end. So what we get is here. We go back, yeah, and the conditional probabilities are 0.8 and 0.2, as you can see. Yeah. 0.8 here, this one, and 0.2. And we write this 0.2. 0.2 times log 2. So, of course, you can calculate these values, insert them, and then if you do this, you get the same result that's written here. It's conditional. Okay, and then I guess this is the last task. I mean, you can now insert this and compare this to this result. This is basically written in the task, yeah. But I don't think that we need to calculate this again. I mean, these values are known, then we multiply this with 0.2. This value, we can do this from here. This is the same as, let's say I have this value at least. This is 0. This needs to be, again, 0.72. Because we had the same numbers before for this h of x, right? There were the same probabilities, and this is 0.7, 0.3. So this is 0.3. And then if you weight these two probabilities, you end up with this value. So, and then the last question, specify the Musha information. As I said, yeah, we don't want to overinterpret now Musha information. We get this later if we talk about channel capacity. And this Musha information, we go back to this graph. This is just this part here. I mark this in this, let's say, orange color. So this here. This is just the Musha information. So this is the information that x contains over y and y contains over x. It's Musha information. We denote this with this I. There are several ways, of course, to calculate this. Yeah. Simplest way, or one simple way, which is often used if we talk about channel capacity. Yeah. We take a look at the entropy here. this output variable, y, subtract h of y given x. In the best case, of course, what can we, I mean, now we can insert values and calculate this. So this is, yes, you're right. It's 0.12. Just check this with my result. Yeah, it's correct. So what does it mean, or how can we interpret this? Let's say we don't talk about this value. Let's say we have a channel, yeah? And let's say, yeah, that we have the entropy of y, it's at, let's say, 1 bit. It's easier to think about such a value. In our case, it's not 1 bit, but let's say it's 1 bit. And then, what does it mean, this conditional entropy? This is the surprise, yeah, in y, so the average information in y, if we know x. And now, if we really interpret this as a channel, what we see here, yeah, this is our channel. Let's say one of the students here is a kind of transmitter, so it just generates zeros and ones, for instance, yeah. And and then there is a channel. It's a noisy channel, yeah. In our case, we could say, so it's quite loud, yeah. There are other students making noise, and I can't hear it, yeah. So, and then he gives me, let's say, a letter, yeah, of the sequence of symbols he generated before, yeah. And I can clearly see this is a 0, a 1, a 1, a 0, and so on. And then I take a look at this, what I really received. And if there is still a surprise, I mean, if he tells me, if a student tells me, I generate a 1, but it's not clear if I really receive a 1. Sometimes I receive a 1, and sometimes I receive a 0. So there is still, yeah, a surprise, an uncertainty in what I receive, even if I know what has been transmitted. This is a conditional entropy. And if the channel is error-free, there should be no surprise in this y. The transmission is error-free. I mean, there should be no surprise in this y if I know x. So there should be, for instance, if we take a look at this diagram, there should be only this path from this value to this value, and there should be no path from here to here, or vice versa. Yeah. And again, here there should be one path in this direction with a probability of 1, so there is no surprise. If I know this, I also know x. But in this case, there is a surprise. So, and later we will prove by this law of large numbers again that it's possible, yeah, to transmit now on average. This doesn't work with a single symbol. If we transmit very long sequences, yeah, of random variables, very long sequences, so we transmit bit streams, for instance, yeah, then we could say on average, if we transmit, for instance, a sequence of 10,000 bits, okay, 10,000 bits, then in the best case, from these 10,000 bits, we can extract 1,275 bits, yeah, which are our original information. These 1,275 bits, yeah, there is the error-free. So, and you may say, but I transmitted 10,000 bits. Yeah, the other bits, so the other 8,725 bits are redundant bits. I need them to basically, redundancy is used to protect transmission from errors, to be able to detect transmission errors from our channel. So I can locate these errors by means of this redundancy, and then I can say, okay, yeah, the decoder basically removes and uses this redundancy, yeah, and extracts the original 1275 information bits. And this is the best case we can obtain, of course. Nowadays, there are coding schemes. These coding schemes are called forward error correction, yeah, which are close to this Shannon, at least for binary transmission. For multi-level transmission, it's much more difficult, this Shannon limit. So, and then, and as I said, yeah, a very known error protection scheme, wait a second, yeah, is, for instance, the Reed-Solomon code, yeah, which is used, for instance, in DVDs, compactors, Blu-rays, and so on. Told you, you can drill holes in this DVD, so, and still you are able to play this DVD. This is, for this, we use this Reed-Solomon code. So, for instance, in fiber optics, yeah, there is a standard, yeah, and the redundancy. I mean, here we would have this is really a worse channel, yeah. We would need to add a huge amount of redundant bits. So from 10,000, only 1,275 would be, in the best case, information bits, if everything works perfect. And in this fiber optical communication, there is a standard for single mode optical fiber transmission. If you add 7% redundant bits, so you have to increase basically your data rate by 7%. Then if on the channel, so at the output of your demodulator, which generates zeros and ones, this demodulator, the error rate is 10 to the minus of 3. Then using this error protection scheme, error probability, the decoder output, it's not 0, but it's nearly 0. It's 10 to the minus of 12 or better. So it's nearly error-free. You had a question, yeah? Yeah? You can basically say, yeah, there is, if you want to interpret this, yeah, you have to generate a long sequence. And let's say, but this is just an example. The first part, yeah, of your sequence, you do this, usually we do this in blocks very often, but not always. There are also so-called convolutional codes. If it's a block code, we could say we use a very large block, and the first 1,075 bits are info bits, information bits. So this is the original information, and we try to transmit this information error-free. And then we add redundant bits, okay? So we add redundant bits, and these are added here. Let's say these are 8,725 or so, yeah? So then the total number of, these are all the X values I'm transmitting. So this is basically X1, X2, yeah? And this is basically X1,000, 10,000, yeah? This is a sequence of transmit symbols. And on average, I mean, don't think if we receive this, we can just delete the red part and then we have the orange part. This is nonsense. This is ensured by clever encoding. This figure shows only the statistics. It shows from 10,000 transmitted bits, we have this number of information bits, and are basically the redundant bits. Redundant bits, but they need to be used. Yeah? They are required to protect transmission. Then, if we have the best decoder for this best encoding scheme, we can extract the original information. But this is very, very complicated. Yeah? The coding schemes are very complicated. I will show you approach basically in 2 lectures, yeah, from now. I show you that Claude Shannon, he showed that it's possible, it needs to be possible theoretically. Because why theoretically? He showed this for very, very long codes, and it's impossible to decode these very long codes by means of a lookup table, for instance. Because these codes are so long, there are so many combinations, it's impossible to decode this, practice. But he showed that this is the theoretical limit. That's the idea. Nowadays, yeah, we have codes which are quite close to this Shannon limit, like LTPC codes, for instance, yeah, or somehow so-called turbo codes, yeah, and this has been possible today, yeah, because we can efforts in signal processing. We can use complex decoding algorithms, yeah, to find the original information. Yeah, but for instance, this Reed-Solomon code, this is quite old, yeah. It was used for the first time, as I know, for the Voyager program of the States. So there's this Voyager space probe, as you know, which is now one of these I think there was Voyager 1 and Voyager 2. At least one is now out of our Sun system from these Voyager space probes. The communication was protected by Reed-Solomon code, or is still protected. This Voyager to the space probe. This was the first application of this Reed-Solomon, I guess. And you can think this was in 1970, whatever, yeah. At this time, yeah, you put all the effort, signal processing in this space probe. And today we have it on each DVD and each Blu-ray, on each whatever. Yeah. Today it's much easier than 40 years or nearly 50 years ago. Okay, so this was this task, yeah, and now we can come to task number 5. This is a quite useful task, I guess, yeah, because in the last lecture there was this question, as I remember, how can I calculate the variance, for instance, of a dice throw? This question. How did you obtain this result? And this is basically task number 5. Try to solve it now. So task number 5. And as you can read, yeah, we consider a game with 2 fair dice. Yeah. And the I sum is modeled as a random variable, which is the sum of 2 statistically independent random variables x1 and x2. So these are the single dice, yeah? x1 and x2. And of course, if you use 2 fair dice, they should be statistically independent. Yeah? And but first we take a look at the single dice, of course, yeah, and then we switch to this sum. Yeah, and we will see that the probability mass function of this sum is just the convolution of the individual probability mass functions. But this only works if the random variables are statistically independent. So I just want to show you some nice features by this task. So A is, let's say we have x1 and x2, and both have the same, of course, probability mass function. So we could say the probability mass function of first dice, yeah, depending for a given value is the same as the probability mass function of the second dice, and we just can use this abbreviation, yeah. So there is no difference between x1 and x2 in this probability mass function. Of course, how does it look like? Yeah. We could say, okay, each result has the same probability. And again, if I draw this in red, so here's 1, 2, 3, 6. We have done this before. Then we could say each value has a probability of 6. And of course, other probabilities, if I draw this like this, yeah, t of 0. It's a function, yeah. So this is 1 by 6 here. So this would be x of x. So we do not need to distinguish between x1 and x2. Yeah. So and then b, determine the expected value, the second moment. So this is the first moment, and we also want to determine variance. Yeah. So we start with this. So there are different names. Let's say I write this like this. So this is the first moment. Here it's just, here I use an abbreviation mu. Yeah, it's easier to write. But this is just the expected value of x. So what is it? The expected value of x. In this case, it's easy because we have equally distributed values. So we could say this is 1 by 6 times 1 plus 1 by 6 times 2 plus 1 by 6 times 3 and so on. Or we can say 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is the same. Then I remember this is 3.5 from the lecture. So this is 10, 15, 20, 21 by 6. This is 3, so 3 by 6 is 1/2. And then we need to calculate, or we want to calculate the second moment, mx2. Maybe you do it on your own. This is the expected x squared. Is it? So we have to square the values and weight them with the probabilities, but in this case they are the same. So see, you can do it. Result, I can see the result again. So this is of course 1 to the square plus 2 to the square plus 3 to the square plus 4 to the square plus 6 6, yeah. And okay, 15, 6, 6, yeah. If, I mean, I have trust in everyone, but I check it. Yes, it's correct. Now the last result, the last question. So what is the variance? What does it mean, variance? It means we can denote this as sigma squared. This is just the expected value of, let's say we take x, subtract the mean. So this is called centralized random variable. New mean is 0. So we subtract this, which is abbreviated with mu in the task. Then I square it and take the expected value. But now let's do this. Why we have a certain relation, these values. Now we could say, I can write this like this. This is the expected value of x squared, right? So this is just the square, minus 2 times x times mx1. And don't forget, mx1 is deterministic. Only x is random. mx1 is just a value calculated before. And then plus mx1 to the square. So, and now we take this expected value. It's a sum. Of course, we can calculate individual terms here. So this is the expected value of x squared minus mx1, 2 times mx1 times the expected value of x. So I can put this outside of this expectation because it's deterministic. Plus x1 to the square. And now the question is, what is this? It's the first moment again, yeah? This is x1. So what we see is we get a result. Here we have mx1 times mx1, and this is mx1 to the square. It's the first moment to the square. So, and then we get that the variance, random variable, is nothing else than the second moment. So this is the second moment. This is minus first moment square. Or in other words, the first moment of a random variable, I square it. If I add the variance, I get the total, so the second moment. And in engineers' language, we would say total power. Of course, at the moment, yeah, we talk about just numbers. The unit of this power is not in watt, yeah. But we could interpret such a squared value as a power level. If we would have units, then we say the total power is just DC power. So this is the DC. Let's say in a signal, the DC component to the square, it's a DC power. Plus, and this is the centralized random variable, so it's the AC power, the second moment of the AC component. So AC power plus DC power is the total power. This is what you have to, I mean, you don't need to do this derivation. You shouldn't. You should absolutely avoid this. You should know this. So we could say, yeah, this is important. You can use this just to calculate this variance. And of course, this variance is, therefore, the variance is equal to So I have to square the, here as you can see, the DC, yeah? 3.5 to the square. So this is quite useful. So now, task number C, determine and sketch the probability mass function of Z. Now I give you some time, and probably you want to do this like this. I would do this, if I would be you, yeah? I would do this like this. I would say, okay, X has some, I mean, rewrite here, Z is equal to X1 plus X2. Then if I would be you, I would do this like this. To obtain all the probabilities of Z, we could say, okay, in this direction, for instance, I write the values of X1. So this is 1, 2, 3, 6. In this direction here, let's say in this X2, I write X2. X2 is again 1, 2, 3, 5, 6. 6. And then in red, yeah, I write the sum. So let's say the sum, Z is the sum of both I numbers, yeah. So the sum would be 2, the sum would be 3, the sum would be 4, 6, 7. This would be, this is one more, right? 3, 6, 7. This is 4, 6, 7. This is 6, 10. This is 6, 7, 10. This is 7. Now you draw the probability mass function of Z, which is easy because now you just have to count the numbers of of a 2, there's only one possibility to obtain a 2 as a sum. 2 possibilities to obtain a 3. There are 3 possibilities to obtain a 4, and so on. And then you can draw this joint probability mass function. Sorry, this probability mass function of Z. So I don't know if it should be if it's like this. See if there's enough place. 1, 2, 3, 6, 7, 8, 10, 11, 12. Oh, yeah. 3, 7, 6. As let's say set. Yeah. So we draw here P set of Z. And now you can do it. Just put the values here in this diagram. Could also say that to make it simpler, you could also say P set of Z times 12. Times how many? 36. There are 36 possible values. But as you want. Maybe I write this like this. Times 6. It's normalized. So I start with 2, yeah, with 1, because the 2 is only in 1 of 36 cases. And the 12 is also in 2 of 36 cases. Let's say. In 1 of 36. So this is 1. It's 2. And you proceed, yeah, for all the other values. Yes, you're right. You're right, of course. It's the 2, yeah. Very good. This is 0 in here again. We cannot get a 13 or 14, 0, and so on. This is, of course, 2. 2 possibilities to obtain 3. There are 2 possibilities to obtain of 36 to obtain an 11. There are 3 to obtain 3 to 10, as you can see. This one. Highest probability is to get a 7. Probability of 7 is 1, 2, 3, 5, 6 by 36. Yeah. So this looks like this. And you see, it's triangular shaped. If you just would draw here such an envelope, let's say, see, this is triangular. So if you think about the original mass function of both random variables, both were, so we have an equally distributed x1 and x2, so we have basically rectangular pulses. And you know, the convolution of 2 rectangular pulses is the triangular pulse. question is, obviously, Z, the distribution of Z can be obtained by doing the convolution of the distribution of x1 and x2. And this is the right result, but we're only allowed to do this if they are statistically independent. And now we can think about why this is the case. So this is what I want to show. P, let's say set of x. Yeah, I can denote this as I want. This is just this number of set, not the value. This is just x1 of x. This px2 of x, or fz or whatever. You can write it as you want. So, and now, why do we get this? We could say we start with, let's say, the 2 here. So how can we obtain a sum which is 2? Then we would say p set of 2, probability that we obtain a 2, we can only obtain a 2 if x1 is 1 and if x2, our second dice, is also 1, the result. So this is the probability. So this is not astonishingly, but you can write now, this is the same as P. Let's say I write this like this. 2 in red. I write here Px1 of our sum 2 minus the value of x2. So if x2 is 1, x1 also needs to be 1. So this is basically, let's say I do it in green, times px2 of 1. So what? We want to show that this is a convolution. This is a 2. Here. Yeah, you can, if you want, you can write as you want. I mean, this, if you want, this is the random variable. But the values can be denoted as you want. You can also write here this as set. Yeah. You can call it as you want. You can call it gamma or whatever. It's just a value. It's a certain realization, a value of this. Okay. So this is now this set or x or whatever. Yeah, I could also write here x, and here I write p set of x. It's also possible. Because it's a certain value. And now let's proceed. How can we obtain a 3? So there are 2 possibilities to obtain a 3. One possibility is x1 of px2 of plus x1 x2 of this. Now I insert these colors. We want to obtain a 3. And then in this case, x1 can be 2. Then, so x2 can be 1. And then x1 needs to be 3 minus 1. Because the sum is 3, right? And then, if x2 is 2, then x1, because the sum should be 3, is 3 minus 2. Then, of course, we can proceed. Yeah. Let's say we write this again for the 4. Set of is equal to px1 of px2 of plus x1 of px2 of plus px1 of times px2 of. Then I can insert again. I want to obtain a 4. Sorry, this was not to do. Here I want to this 4 and here this 4. And then, yeah, x1 can be 1, for instance. Then, or x2, sorry, can be 1. Then x1 needs to be 3. So 4 minus 1. x1 can be 2, then this is 4 minus 1. And it can be 3, and then this needs to be 4 minus 3. Right? So, and if, let's say, x2 would be 4, then we could also insert here the probability that x1 is 4 minus 4, and this is 0. Yeah? This probability. So we could even insert here different values, and you see immediately that this is the, what is it mathematically, what you see here? What is it? It's a convolution. This is nothing else than the convolution. So we could say, now if you want, I write this with set. Yeah. So I say, therefore, p set of set is equal to sum. So of course, I can start with this x2, maybe it's in green, this green, yeah. So x2 goes from 1 to 6. There are no other values for this x2 which are possible. And then I write, then I need to take a look at x1. So this is x2, the value of x2, yeah. And then I insert here p x1 of this set value, so set minus this x1 or x2 value, right? Times x2 of x2. This is exactly the convolution, yeah. Which you may know not in this discrete form, yeah, but which for continuous time signals. So this is usually, if you write this for continuous time signals, this could be in a time domain. This could be t. Yeah? This could be tau, t and tau. Instead of a sum, you use an integral. And the short version of this is, of course, this is just a discrete convolution. This is equal to px1 set. This is the convolutional operator px2 of. If you need to calculate such a convolution, yeah, then you write, of course, we could also insert here all the other values, yeah, this x. But we don't need, because these values are 0, if you insert other values than 1 to 6, but we could do this. Yeah. That's quite interesting. And now you could say, maybe you have an idea. Now if you do the convolution, yeah, of 2 rectangular pulses, get the triangular pulse. Now let's say this envelope, how does it look like? What is your thought? If I use now 1,000 dice, 1,000, and I take a look at the sum, I get the convolution of 1,000 rectangular shaped envelopes. What do you think? How does the probability mass function nearly look like? What is your No, it would be compressed if you divide by this 1,000. You are right. But now we don't compress this. Yeah, you're absolutely right. It's correct. But we don't compress this. So the lowest number would be 1,000. Highest number would be 6,000. And all the values between are possible. But how does it look like? Nearly. No, it's not a delta function. No, it goes from 1,000. The next possible value is 1,001. 1002, 1003, all these values are possible. And there's another value, and we know the probabilities. These are easy, of 6,000. But how is the shape? Clearly. So you do a convolution of 2 rectangular pulses, then you do the convolution of this with a rectangular pulse, again a convolution with a rectangular pulse. Probably it's again the case that these extreme values have a low probability, yeah? And just in the middle, this has the highest probability. But what do you think? Is there any idea? Have you heard about what happens if you have a large number of random variables or which contribute to a random variable? Could say we take a look in a wire, yeah, and there are a lot of electrons, huge number of electrons. Definition of temperature is if we temperature which is larger than 0 Kelvin, there is a movement in these carriers. As they move, this is stochastic. But it's a huge number of electrons which contribute. So this so-called thermal noise, there is a huge contribution of individual electrons. Do you know how this thermal noise is distributed? Binary. Gaussian distributed. It's Gaussian distributed. This is basically always true. If you have a huge number of contributions to a random, so additive contribution of statistically independent things, you end up in a Gaussian distribution. Yeah? And you can, this is why I said, just use maybe Octave or Python, yeah, which I mentioned here, this program. So if you take a look at this distribution function,